All right, so let's take a look at circuit safety. And before we look at the devices that help keep the circuits safe, let's talk about what probably is going to cause the problem in a circuit. And that is either a short circuit, or it doesn't even necessarily have to be a short circuit, but short circuits create a similar kind of problem. And let's take a look at what that would look like. So I'm going to draw a circuit here, and it's going to be a parallel circuit. On one side, we'll have a light bulb. All right, so basic circuit. What I did was to put a switch into the circuit. And the reason why I put that switch in there is so that we can have two different settings. So one in which the switch is open, and in that case, this light bulb is going to come on. It will have the same voltage as the battery, and the bulb will probably be pretty bright. Now, as soon as I close this switch, the bulb's going to turn off. This bulb's going to turn off. It will not produce any light anymore. And it's not because it's not getting any current, but it's going to get very, very little current. Because as soon as I close that switch, I will have created a second branch which has basically no resistance. There's virtually no resistance. So imagine this had a resistance of 100 and this had a resistance of 1. Well, this guy would then get 100 times more current than the other guy. But it's actually much worse than that. This short circuit, right? And it's, look, it physically is shorter because of where I drew it. But I could have put that switch over here on this side. Okay, so the word short doesn't necessarily mean that the path is shorter. It simply means that you're giving an alternate path that's going to allow it to skip one of the elements in the circuit, and therefore that circuit element is probably going to stop working because it's going to receive so little current that it can't function correctly anymore. And that is certainly the way that the light bulb is going to work. So a short circuit is any circuit that has little or no resistance. Okay, now that's obviously a nuisance because when I close the switch, it's going to seem like I somehow shut the light bulb off because the light bulb's not going to function correctly anymore. And that's when you use that term, you say something was short-circuited, it means that you basically you did something that allowed that thing to become disabled so that it could no longer function correctly. Now, here's the real dilemma. The problem is not that this light bulb is not going to come on or that it's not going to function correctly anymore. The problem is that as soon as I close this switch, I have now created a circuit which has virtually no resistance, and that means it's going to pull a lot of current. Because remember that the current I is equal to V over R. So the relationship between the resistance and the current is inverse. Right? I mean, look at the way the equation is written. I is equal to V over R. The bigger R gets, the smaller I gets. But the smaller that the resistance gets, the bigger that I gets. And we're not talking about making a small difference. We're not talking about going from 5 ohms to 4 ohms. We're talking about going from 5 ohms to no ohms. Right? So there's no limit to how much current you can draw. And the reason that's going to become a problem is because, as we have talked about, when you pass current through any object, it's going to heat up. When you pass a lot of current through an object, it's going to heat up a lot because those random collisions with those moving free electrons delivering some of their energy to the atoms is going to cause those atoms to get so hot that they will reach hundreds of degrees. So the wire, there's really no limit. You could make the wire so hot that it melts. You could literally bring that wire up to thousands of degrees so that the wire would melt. It is not difficult to do. And I've seen students, even with just a battery, a light bulb, and a wire, I've seen them burn themselves. Because what they do is they don't even put the light bulb in, or they don't connect it correctly, so they basically have just connected a wire to a battery. And now the battery starts to get really hot, the wire is going to get so hot that it will burn you. You will definitely feel it. I assure you, if you try that at home, I would recommend not doing it because it's kind of painful, but it's probably not going to kill you. If you just connect the wire to a small 1.5 volt battery, you'll see that it's going to get hot quick. You'll disconnect it very rapidly, I assure you, because you're going to find that wire gets super hot. So here's the dilemma. right now I'm drawing a circuit, and this is something that we're doing in the lab. But in reality, these wires would be hidden inside your walls. And also inside your walls is lots and lots of dust, which has collected over the years. Small openings in the wall and just the inside of the walls disintegrating is going to cause a collection of dust. Now today, we don't just let the wires run through the walls and they just hang there like that. They are protected in a plastic coating, and typically they're going to be in some kind of steel conduit, and that's going to keep the dust off of them. But look, if the wire gets super hot, then the steel conduit will also get very hot. And so the potential danger that the dust will catch on fire is very great. And this has been the source of many, many fires when electricity was first becoming common in people's homes. Was that they would pull too much current. They would either create a short circuit, or they just would draw too much current, and that would cause the wires to get so hot that they would start a fire. And what's so insidious about those fires is that you won't see it right away, because it will not be visible to you. It's going to be inside the wall. You're not going to hear it. You're not going to smell it until finally there's so much smoke and flames inside there that the smoke starts to escape through small holes in the walls. And at that point, you still might not know where the fire is. You might just simply notice that there's smoke in the room now that you had not noticed before, but you don't know where it's coming from. And you would have to literally kind of move around the house and try and see, like, is there one of these walls that's really hot? And yes, one of them will be very hot. And so oftentimes this would happen with space heaters. This is like one of the most common ways that people will end up killing themselves, is because they put several space heaters. The space heaters all kick on at once, and they draw so much current that they heat up one of the wires inside the wall of your house to the point where it catches on fire. And that fire will probably not be detected until the wall is completely engulfed in flames. And at that point, there's probably not much chance that you're going to be able to put it out, because the wall is going to be so hot from burning quietly on its own that even if you put water on it, the water will evaporate. And so you may not end up being able to put that fire out at all. So people very early on realized, well, we have to do something, not just for short circuits, but just in general, to make sure that people don't plug too many things in to the point where they start to draw too much current. So let's just add this before we talk about the 3 safety devices. Too much current equals possible fire. So this is what we want to eliminate. We want to try to eliminate that. Now also, it's possible that if too much current goes to a certain electrical device, it might cause damage to it. It might exceed the amount of current that is able to flow through that without damaging it. And so what I'm about to show you as these safety devices does both, basically. It prevents the big currents that might start fires, and also protects the sensitive electrical equipment from having too much current that might cause it to be damaged, even though it doesn't necessarily catch on fire. So first there is the fuse and the circuit breaker, and they both do the same thing. And that is, they stop the circuit from getting too much current. So the way the fuse works is there's a couple different fuses. Fortunately, you don't have to deal with these in your house anymore because we use circuit breakers. But in your car, there would still be fuses. There's no circuit breakers in your car. So the fuse is a great device. I mean, it's really ingenious, but it does have a kind of a flaw. So let me show you what a fuse would look like. Typically, they look like this. You don't need to draw this. Okay, so that is typically what a fuse would look like. Here's an actual fuse. Oh, look, I almost drew it the same size. That is the fuse from Christmas tree lights. And the reason why Christmas tree lights have a fuse inside the plug, I'm saying when you plug into the wall, that part that's in your hand, when you plug into the wall, if you look at it closely, you'll probably find there's a little panel that opens. And inside of it is one of these guys. Now, it depends on the lights. Not all lights will have them, but most of them should. And the reason is because we want to be really careful not to put too much current through Christmas lights, because if they get too hot and they're wrapped around a dry, dead Christmas tree, of course, they're going to cause a fire. So very important that those things are not allowed to ever get anywhere near a large current in there so that they don't cause a fire. Now, the problem with these things is that if you did exceed the current level, it would actually break itself, because essentially all this device is a very, very thin wire. It's usually made out of tungsten or some other similar type of metal, and it's connected to the metal cap on both sides, and then it's glass, so you could look inside. I can see inside. I know you guys probably won't see this on the camera, but I can see inside and I can see the wire. What am I trying to do here? Yeah, I don't think I can get it to focus. Nope, I don't think you're going to be able to see it very easily, but there is a very thin wire in there. And essentially the way it works is the diameter of the wire is so thin and so small that it creates a lot of resistance, right? Because the smaller cross-sectional area creates a lot of resistance. And so when the current passes through there, they put this guy in parallel with the other so that if he begins to draw too much current, it will melt. It will melt the wire. The wire will literally get so hot for just a split second that it will melt, and then that wire is broken, so the current can no longer go through there anymore. Now, the problem obviously is that it's broken, so now you have to actually take it out and put in a brand new one. And so people would have boxes of these fuses at their house, and obviously, you know, there were times where people would run out of the fuses, and it would be late at night, and they couldn't go to the store and get it, you know, so they had basically messed up, and they didn't get the stuff in place beforehand. So then what people realized was that for something like this, it's like a little clasp. So this guy sits in, and then there's like a little clasp, like it just kind of clicks in and holds it in place. And what they would find is that if they took like a nickel or something, or maybe they took like a little stack of nickels, maybe 2 or 3 nickels or something like that, and they pushed them together, they could push it into the spot where the fuse was supposed to go, and then everything would come back on. All the electricity would come back on. But obviously now there's nothing there to stop the big currents. So those same people who would do that probably end up killing themselves, because then the currents get super high again, and there's nothing to stop the fire from starting. And essentially, this is probably going to happen while you're sleeping. You know, at night, while you might have space heaters or things on, with too many of them, and without these safety devices, you could potentially catch your house on fire, and you'll be asleep. You won't even notice it until it's too late. You might even never even wake up, because so much smoke fills the room that you lose consciousness before you even notice that there's a fire. So I drew this fuse because this is probably what most people are used to if you've ever seen a fuse before. But the fuses in your car kind of look like a postage stamp. And they basically, it's like a square. You can see the wire. The wire is right there. It's connected to 2 little metal teeth. And the little metal teeth just stick into like a panel. And there'll be, you know, dozens of them in there. And you can pull them out and replace them if you find that something has burned out. So I'm not going to try to draw the circuit breaker because I'm just not that talented to be able to do it. But I can show you a picture of what a circuit breaker looks like, I hope. Let's see if I can get this book in here. All right, so there is the circuit breaker. Now this device is ingenious because it doesn't have to break itself in order to be able to turn the electricity off. Let me see if I can put this in place. Okay, so basically the way it works is they take 2 pieces of metal and they marry them. I swear that's the word for it. When you connect 2 pieces of metal together and you fuse them together, they are referred to as being married. But you take 2 different kinds of metals. And what you want is 2 different kinds of metals that will expand differently when they heat, because all objects expand when they heat up. Okay, that's just a basic principle of our universe. If you heat something up, it expands. If you take a balloon, for example, and go put it in your refrigerator, leave it in there for a little while, and then take it out, you'll see it got smaller. It contracted because it got cooler. You leave it outside on the counter, come back and check on it a little bit later after it's warmed up, it'll be bigger than it was before because it will have expanded. So what you want is 2 different pieces of metal. Let's imagine that my right hand expands more rapidly than my left hand does. Well, when I connect these 2 together, even though my right hand is trying to stretch and get longer as it expands, as it warms up, it can't go anywhere because it's connected to the other piece of metal. So what will happen is, as my right hand expands and my left hand doesn't expand as much, the piece of metal will begin to bend like this. Because you can imagine my right hand is now following a longer path than my left hand is. So essentially, this thing is referred to as a bimetallic strip because it has 2 different kinds of metals. And as it expands, as it allows the electricity to pass through, it will heat up. It will begin to expand, but asymmetrically so that it will begin to curve. And I swear to you, it curves until it pushes this switch. This piece right here will bend towards the switch until it shuts it off. It literally reaches and pushes and shuts the thing off. And of course, as soon as the current stops, it relaxes. So instead of pushing, it relaxes back to its original position. And all you need to do is take the switch, reset it, and pull it back, and it will come right back on, and everything will work just as good as it did before. Unless you didn't unless you failed to disconnect one of the electrical devices, in which case it's going to flip right again. So obviously, before you go down and check your circuit breaker, you want to disconnect some of the things that you had connected. You have too many things connected to that outlet or that that section of your, you have a very large circuit, electrical circuit in your house, and you've overloaded a portion of it. And so you want to disconnect some of that material. Okay, so that is the circuit breaker, and both of the circuit breaker and the fuse are designed to prevent fires from occurring. Okay, so the last device then is you can be electrocuted. And that is where we developed this device called a ground fault interrupter. So that's pretty interrupter. I think there's 2 R's. Yeah, probably. Okay, so the ground fault interrupter, you have one in your house, I'm sure. It's probably in your bathroom. Maybe you might have it in your kitchen also. It's essentially, it looks like a regular outlet. You have your 2 places where you can plug things in. But in between the 2, you'll see that there's 2 buttons. And those 2 buttons are to reset the ground fault interrupter. So let me show you a picture in case you're not sure what I'm talking about. I don't know why I closed this book. I meant to show you this picture. So there it is. That's the ground fault interrupter. Okay, so this is a special kind of outlet which has this ring that is measuring whether the current that's coming in is equal to the current that's going out, because it certainly should be. The current that goes in should be equal to the current that goes out. Otherwise, charges are escaping, right? I mean, if 1 amp is coming in and only half an amp is coming out, well, then where did the other half amp go? Probably someplace that it shouldn't have gone, like maybe this guy. So the place where this is going to be most dangerous is anytime you have an outlet that's near water. Because water, while it is not a good conductor of electricity, it normally has lots of dissolved things in it which are good conductors of electricity. And so when water splashes on this, it creates a possibility that sparks may come out and cause a fire. Or you might be connected to that water, and now the water connects the current from the outlet, and you get electrocuted even though there was nothing plugged into the outlet. So what this device does is it looks at the current coming in and out, and if they even vary the tiniest, slightest, even micro amp different between the incoming and outgoing, it just says that's not right, and it shuts itself off. Something is going wrong, and it shuts itself off. And so it breaks. It uses an electromagnet to pull up and break the break the current, because now there's this break in the wire. You push the button to reset it. It pushes everything back into place. And as long as there's no more water drawing current from that thing, then everything should be fine. And according to this book was written in 2005, the process to break the circuit only takes 0.025 seconds, so less than 3/100ths of a second, in order for the current to be stopped. This is a thing where people, for example, like they might be, someone's taking a bath. Okay, and so not only does the water already have dissolved things, but now you have lots of salt on the surface of your skin, and it's dissolving into the water, making it a better and better electrical conductor. Now, somebody else is in the bathroom with you, and they are drying their hair with a hairdryer, and they bump themselves with their head, and it falls into the bathtub. That person in the bathtub will be killed, for sure, without that ground fault interrupter, because that water is now going to begin to draw huge currents, and you're in that water, and you are going to be electrocuted. And there's really almost no way to do it. The only thing you could possibly do is try to pull the hairdryer out by the cable without touching any part of it, because otherwise you're going to get electrocuted. So people even committed suicide this way, which is a really, really awful way to commit suicide. I mean, it must be so painful. And so people realize that we have to do something to protect people. We need to make it impossible for this thing to happen to anybody. And so that's where the ground fault interrupter was born. If you look at your hairdryer, it probably has a ground fault interrupter built into it. That's how worried they are about hairdryers. Even though modern bathrooms, it's required by law to use these in bathrooms. But some people still, old houses might still not have been updated, and maybe they don't have those. And so they built a ground fault interrupter directly into the device to make sure that that device could never fall into a bathtub or a sink and electrocute the person. So that's different than the other safety devices because it's not about starting a fire. It's about making sure that no electricity is escaping that could be harming somebody directly. Forget about the fire. And those are the three main safety devices.